We're going to run through an example of the transformer architecture. The visual that pops into most folks' minds when they think about the transformer architecture is this image from the original paper in 2017. What made the transformer architecture so revolutionary, though, really is the implementation of self-attention and the attention layers. While this is the visual that pops into most minds, the transformer can actually be implemented a few different ways. The original paper introduced the transformer via an encoder-decoder architecture, primarily because it was predominantly focused on machine translation. Shortly after, though, in 2018, Google introduced BERT, which was an encoder-only implementation of the transformer, and OpenAI introduced GPT, which was a decoder-only implementation of the transformer. My goal for the remainder of the video is to leave you with a complete understanding of the original transformer architecture, as well as its respective encoder and decoder-only implementations. So let's get started with an example that we'll use throughout the video. Let's assume that our input is beam me up. This input will be fed into the tokenizer, which has two functions. First, it takes our input string and chunks it up into logical subcomponents, or tokens. Every tokenizer has a token array and token vector that basically acts as a dictionary for the tokenizer. Let's assume that our tokenizer breaks up our input sequence into three tokens, beam, me, up, respectively. The tokens in a tokenizer are dependent on the model it's intended for. If you have a coding model, then it probably makes sense for your tokenizer to have tokens such as DEF or int or str. Whereas if you just had a generalist chat model, maybe it doesn't make sense for your tokenizer to break up a token specific to str. Keep in mind, though, that once the model is trained, the tokenizer that was used during training is inextricably bound to it. It cannot be swapped out for another tokenizer. Now, after our tokenizer has chunked up our input, it will then look up each token respectively in the list of tokens and return its respective index. A tokenizer will literally have a list of 25, 50, 100, 1,000 tokens, all of which, of course, correspond to a specific index. To continue with our example, let's assume that beam me up are at indices 111, 222, and 333. All right, we now have a complete tokenizer. So, just to recap, it takes in an input string, chunks up that input into logical subcomponents, known as tokens, and returns those indices in a vector of size s, where s is the number of sequence tokens. Now, we send this vector to our embedding layer. Not unlike our tokenizer, our embedding layer also has a dictionary of sorts, except now that dictionary is in the form of a matrix, and we are mapping these indices, these input indices, to their respective row vectors. Each of these row vectors are representations of the original index in a higher dimensional space. Now, your embedding lookup differs from your tokenizer lookup in a sense that these numbers aren't random, or that these numbers aren't arbitrary. The original index of apple or banana or carrot doesn't really matter as long as that index stays the same post-training. But these numbers in the embedding layer were trained via an embedding model to understand the relationship between respective tokens and represent them in vector space accordingly. Now, we can't visualize this in high dimensional space, but we can in 2 or 3 dimensions. The classic example is if we had a 2-dimensional representation of 4 input tokens. Let's assume our tokens were king, queen, man, woman, respectively. We can visualize these tokens on a 2-dimensional chart like so. If these X values were trained to maintain the relational integrity between these tokens, then you can see how by subtracting man from king and adding woman, you actually end up close to where queen would be. Now, we can infer that this token represented at 1-1 has something to do with royalty or being royal, just based off of its relationship between man and king and woman and queen, respectively. Feel free to pause this video to digest how these tokens have relational context. Okay, so to summarize, our embedding layer takes in an input of a vector of size s, where s is the number of sequence tokens, and outputs a vector for each respective input token of size 1 by d, which can be viewed as a vector of vectors, also known as a matrix. For our example, we're going to trivially assume that our embedding dimension is 8. However, in application, it's really much larger, whether that's 1024, 2048, 4096, etc. We are now officially past the input embedding. And so let's touch on the positional encoding for a brief moment. Similar to how we visualize relational context in vector space, the easiest way for us to understand positional encoding is also with two dimensions. Let's assume that our tokens have the following x0 and x1 values. Beam at 1, 2, me at 3, 4, up at 5, 6. Remember that these x0 and x1 values would be the output from our embedding layer, assuming that our embedding layer had a dimension size of 2. Now let's assume two different initial inputs to our embedding layer, and then view how they would be graphed with and without positional encoding. The first input is beam me up, represented by 111, 222, and 333, and the second input is me up beam, represented by 222, 333, and 111. Since the default starting vector for each token provided by the embedding layer is respectively the same, both of these inputs would result in the same initial vector landscape. Now, intuitively, most human languages read left to right, and so at first glance, it doesn't make sense to us why the model would not recognize that different graph coordinates are at different indices. But models don't digest embedding representations left to right. It's better to visualize it as if it's absorbing the entire blueprint all at once. And instead of focusing on our numerical vector of vector representations, we have to look at the graph. And when we look at the graph, it's quite apparent that both blueprints get absorbed or digested by the model identically. Now, the sequence me up beam doesn't make any sense. I mean, nobody would ever say that. But briefly, let's just assume that our tokens were dog bites man. If our input actually was man bites dog, those two sequences have completely different meanings, and it doesn't make any sense for our model to initially view and represent them both as the same sentence in vector space. To address this, we will demonstrate positional encoding so that our model can start with different blueprints to address these two different sequences. At a high level, positional encoding is nothing more than adding some value to each respective token so that it's able to represent itself differently based off of where it is in the sequence. Imagine if we just linearly added the respective position of each token to its embedding dimensions. This would result in objectively two different initial blueprints for our model to work with. Now, in this trivial example, the fact that me and beam are encoded as 3, 4 in the second sequence would be a significant problem because you, of course, would never want two completely different tokens ever pointing to the exact same vector representation. However, this example isn't realistic for two reasons. First, it's only two dimensions. As we discussed, models will have dimensions into the thousands. And second, simply linearly adding the position to each index is good for a quick visual, but it isn't practical for an actual implementation. The proper, but complicated, way to positionally encode your sequence is to run each positional index of each token at each embedding dimension through what is called a deterministic sinusoidal function. This will result in a value between -1 and 1 to be added at each index of each vector. Now, the value of leveraging the deterministic sinusoidal function, as opposed to just linearly adding additional values to each next token like we've done, is that by adding a bounded range between -1 and 1, it prevents the positional information from overwhelming the semantic content of the token embedding. For example, at the millionth token, if we were to linearly add 1 million to 6, the positional encoding of that embedding dwarfs the actual trained embedding, and thus you lose all context. Since sinusoidal positional encoding always adds a value between -1 and 1, it ensures that every token maintains its contextual integrity, regardless of how far along in the sequence. To complete our example, if we properly positionally encoded our above two input sequences, the result would be as follows. Notice how the result maintains the contextual integrity of both input sequences.